We're continuing to discuss the concepts related to stereochemistry. In this video, we are going to be talking about enantiomers, diastereomers, and racemic mixtures. And all of this is related to the chapter haloalkanes and haloarenes, and all of this actually started because we talked about SN1 and SN2 reactions. Definitely let me know if there is a specific topic that you need help with, or like a specific question that you are finding difficult. Let me know. So, enantiomers, diastereomers, and racemic mixtures. Till now, we've spoken about what a chiral carbon is. A chiral carbon is the one which has four different substituents attached to it. And usually, a compound that contains a chiral carbon is optically active. An optically active compound is the one that is able to rotate the plane of polarized light either to the right or to the left. Now, we've spoken about all of that over the past couple of videos. Definitely check that out, to get a better understanding about those concepts. But in this one, we're going to be specifically focusing on enantiomers and diastereomers. Now, I know diastereomers is not something you learn in your text. I mean, it's not something that's discussed in your textbook, but I felt like it's essential for you to know, and it's like a good thing to understand. And I'm sure that probably comes up in your, the entrance exams that you're preparing for. So we're going to be talking about only one specific compound. We're talking about 3-bromo-2-butanol. So butanol, which means it'll have 4 carbon atoms. Okay, and at the third position, you have the bromine atom, and at the second position, you have the OH group. Okay, so this means it'll have a H here, and it has CH3 and CH3. Now, this automatically implies that this carbon and this carbon are both chiral. Okay, that's because they have 4 different substituents. Now, what we care about is the arrangement in 3-dimensional space. Honestly, I found this example on one of the websites. I'll put the link to that as well in the description below. So, let's start with drawing the structure of the 3-bromo-2-butanol. Okay, so first one we're going to do is have oh, okay. And that. So this implies there's a second carbon, there's a third carbon. Okay, and both these carbons have the substituents going behind, right? So the wedge dash representation, the wedge is coming towards us, the dashed one implies it's going away from us. So this is one of the first ones. So here, oh, actually, it's not OH on the third carbon, it's actually bromine. Okay, so you have the bromine and the OH. Now, let's assume you have a mirror in the center. So the mirror image for this particular thing would be just flipped, right? So if it flips, you would have this carbon would be at the top, and then you'd have a straight line representing these 2 carbon atoms, or like the bond between these 2 carbon atoms. And then since it's a mirror image, you're going to have it flipped like that, right? And your OH, so this is going to be your Br, the bromine atom. And you're going to have your OH over here. So here, if you notice, both of these are mirror images, but when you put them one on top of the other, they are not superimposable. So enantiomers are non-superimposable mirror images. So this and this are enantiomers because they're non-superimposable, but they are mirror images. So when you put this on top of this, you won't be able to it's not superimposable, but it is a mirror image. Now, another way for us to write the same compound is basically, so you have, this is your main carbon structure, the 4 carbon atoms, and we're going to assume that you have the bromine atom, going behind the plane, and you have the, oh, that was bad. The OH atom, OH, the hydroxyl group that is coming towards us. Okay, so this so this basically implies that this is coming towards us and the bromine is going away from us, right? Now, when you have a mirror plane in between the two, let's draw the mirror image for this. So you'd have the same carbon structure, right? The four carbon atoms, and the bromine is going to be on this side, and the OH is going to be on this side, hydroxyl. Okay, so here also this and this, they're both non-superimposable mirror images. So essentially, each of these pairs are non-superimposable mirror images. So they are enantiomers. Anything which is a stereoisomer but is actually, honestly, this is the definition I found everywhere else where they talk about diastereomers as the ones which are not enantiomers are diastereomers, and that's a really broad definition. What I like to go by is that they're non-superimposable non-mirror images. Now if you think about this, all of these, so let's call this 1, 2, 3, and 4. So 1, 2, and 3, 4. These are enantiomeric. They are enantiomers, right? Because they are non-superimposable mirror images. 1, 4, 2, 3, 1, 4, 2, 3, and 1, 3, and 2, 4. All of them are non-superimposable, non-mirror images. So they are diastereomers. Essentially, they have which are not enantiomers, they're considered to be diastereomers. That is what you need to understand. So enantiomers are, so if you have a pair of enantiomers, they typically have the same physical properties, they have the same chemical properties, but the one important difference between two enantiomers is the fact that they rotate the plane of the polarized light in the opposite directions. Again, we've established that you cannot figure out which direction they rotate the plane of polarized light. But if, let's say, one is rotating it to the right, then the enantiomer 2 would rotate to the left. So enantiomers have similar physical properties, but the one thing that they have different is that they have um, they rotate the plane of polarized light either to the right or the left, and they're opposite to each other. So that is all. Now, when you have a mixture of, oh, I don't know what happened, but oh well. So let's say you have, oh, okay, I'm giving up. So let's say you have equal amounts of 1 and 2. Okay, and we're going to assume 1 rotates the plane of polarized light to the right and 2 rotates it to the left. This is an assumption. This is not the truth. I mean, could be the truth, but this is just an assumption. So if you have equal amount of 1 and 2, then they would rotate the plane of polarized light to the right and the left respectively to equal extent. So when you have equal amounts of both the enantiomers, it is called a racemic mixture. What is it called? It's called a racemic mixture. When you have equal amounts of both the enantiomers, they tend to rotate the plane of polarized light to the same extent but in the opposite direction. So this means that they are a racemic mixture, and racemic mixture usually are not racemic mixtures are, I mean, they're going to show zero optical rotation. Now, the process of conversion of an enantiomer into a racemic mixture is called as racemisation. So when you have just one of the enantiomers and then you get to a point where you have equal amounts of both of them, that process is called as racemisation. So in the next video, we are going to be discussing the example problem given to you in your textbooks. It's pretty straightforward, but definitely check that out.